In this video, we're going to do another example of determining the molecular formula from the name of an ionic compound. Here we have aluminum oxide, and that is probably the most complicated it gets when determining the molecular formula from the name of an ionic compound. So again, the naming here, the naming system for ionic compounds does not tell us specifically how many aluminums and how many oxygens we have. We have to figure that out using the Lewis structures of each compound. There's other methods as well, which we'll go through in future videos. But using this method, we want to draw the Lewis structure for aluminum and the Lewis structure for oxygen. So aluminum, again, has 3 valence electrons, and oxygen has 1, 2, 3, 4, 5, 6 valence electrons. All right, if I go ahead and actually I'm going to move this electron right here, just to make it a little bit easier to draw. If I go ahead and connect the dots, show the transfer of electrons, if I show that this electron might go right here, this electron might go right here, well, let's look, and we have an extra electron. If we have any extra electrons, that means we either did something wrong, or more likely, it just means you need to add another element. So this electron right here, it needs to attach to something. We don't like freestanding electrons. They need to be given up. Again, as a reminder, aluminum has 3 valence electrons, so it is only interested in forming an ionic bond if it can get rid of all 3 electrons. If it can only get rid of 2, it is not interested whatsoever in forming a bond with only getting rid of 2 electrons. It is only interested if it can get rid of all 3. So this extra electron right here tells us that aluminum is not interested in forming a bond with a single oxygen. Maybe we need more oxygens in order for that extra electron, to be given away. So let's draw another oxygen here and see if we can get rid of that electron. All right, so we have this electron, and we're just going to donate it to this oxygen right here. And that solved the problem with aluminum. Aluminum has now given away all 3 of its electrons, so the aluminum is happy. However, you might notice that we have an extra electron right here now. And oxygen, just like aluminum, is only interested in this transaction of electrons if it can accept 2 electrons. Oxygen is not interested whatsoever in accepting only 1 electron. It wants to accept 2 electrons, and if it can't accept 2, then it's not interested at all whatsoever in forming an ionic bond. So this extra electron right here, just like aluminum, tells us that we either made a mistake or we need to draw another atom. So let's draw another aluminum and see if we can figure out if we can get an electron, another electron donated to this oxygen. So aluminum again has 3 valence electrons, and let's go ahead and start donating them. So we've got, we can donate this electron right here to this oxygen, and now this oxygen is now happy because it has accepted 2 electrons. And it is now at its valence number of 8. It has 8 valence electrons, so it's at an octet. It is very, very happy now. This aluminum is already very, very happy because it gave away all 3 of its electrons. And this oxygen right here is very happy because it accepted 2 electrons. So all 3 of these atoms are now happy because they have accepted or given away the correct number of electrons so that they can get to an octet. However, let's look right here. We have an electron here and an electron right here that both are not attached to anything. We need to do something so that these electrons can be given away, because as I have mentioned before, and I'll keep mentioning, aluminum is not interested in giving away only 1 electron. It is only interested if it can give away all 3. So again, these extra electrons tell us that we either made a mistake or we just haven't finished drawing this. And so let's draw another oxygen and see if we can solve the issue now with aluminum and giving away those electrons. So oxygen has 6 valence electrons. And let's see if we can donate these electrons and make everybody happy. So this electron can go right here, and this electron can be given right here. Right here. So now, if we go back through everything, both aluminums have given away all 3 of their electrons. Every oxygen here has accepted 2 electrons each. Therefore, everything's happy because the aluminums, both of these aluminums have now reached an octet, and all 3 of these oxygens have now reached an octet. We just needed a multiple of each of these elements in order to form that, but that's totally okay. And everybody's happy in this transaction of ionic bonds. So let's go ahead and show what this looks like when we draw a Lewis structure of it. And then we will show what the ionic compound's molecular formula is. So when 2 aluminums bond to 3 oxygens, again, we're going to draw aluminum when it gives away its electrons. We're going to draw aluminum in brackets because it now has a charge. Anytime there's a charge, we're going to draw brackets. And then outside the brackets in the top right corner, we're going to indicate the charge. Aluminum lost 3 electrons. It lost 3 electrons is the number that it lost. And then we said that it lost them. So it now has more protons than electrons, so it has a positive charge. And then we have a second aluminum, and it has a positive 3 charge. And then we have 3 oxygens. And this one's kind of tricky to draw, so I'll show you a shortcut method also, but we're just going to draw the positive charges and then the negative charges, just kind of lines together. But so we've got oxygen with 8 valence electrons because it accepted 2 from aluminum. So I will draw that, and I'm going to draw these electrons that it got from the aluminum in a different color. There we go. And then we will put brackets around it because it is now charged. Oxygen normally has 6 valence electrons, but it accepted 2 more. So with 2 extra electrons, it has a -2 charge. And then I'm going to copy and paste that 2 more times because we have 3 total oxygens. So let's make it a little bit smaller. And then we have our 3 oxygens next to the aluminum, or next to the 2 aluminums. Something that I do want to point out here that I forgot to point out in the last video is let's look at the overall charge that we have on this side of the equation, and or this side of the reaction, in the reactant side, and then let's look at the overall charge on the right side, on the product side. So let me erase these arrows just to make it a little bit more easy to see real quick. All right. These aluminums here, do they have a charge? No. And these oxygens right here, do they have a charge? No. So the overall charge on this side is 0. Now let's look over here. We have a +3 charge. And then we have another +3 charge. But then we have a -2 charge, and a -2 charge, and another -2 charge. And if we add all that up, we're going to do 3 plus 3 minus 2 minus 2 minus 2. That's going to equal 0. If there is no charge on the left side, that means there needs to be no charge on the right side, or an overall charge, a net charge of 0. Because law of conservation of mass, which we'll learn about another time, says that we can't just magically, sporadically create something. Mass is never created nor destroyed, and that's going to be the same thing for electrons or anything. So we can't magically create or destroy electrons. They are there or they're not there. So if we need the same number of electrons on this side of the equation as we have on this side of the equation. So you can check that by checking the charge on each side of the equation. And then lastly, let's go through the naming of these. So we have here 2 aluminums and 3 oxygens. We can count that there are 2 aluminums and 3 oxygens. So we're going to write down the formula aluminums and oxygens, but we don't just have one of each. We have 2 aluminums and 3 oxygens. So our formula is Al2O3. Again, these numbers in the subscript tell us the number of each element that we have. So Al2 means there's 2 aluminums, and O3 tells us that there are 3 oxygens. And so that is what aluminum oxide represents, Al2O3. All right, and then lastly, if we don't want to draw out the whole formula like this, there's kind of a quick method, a shorthand method of drawing it, where we could say that we have aluminum we could say that we have 2 times aluminum, the +3 charge, and then 3 times oxygen with, oops, I copied that oxygen. 3 times oxygen with a -2 charge. So that's just another way to write it. But yeah, there we go. That's probably the most difficult example there is, aluminum oxide. But again, you just keep adding more of, so with aluminum, we started with aluminum having an extra electron, so we added another oxygen, and then we had to add another aluminum, then we have to add another oxygen. You just keep adding elements until it balances out to where every electron is given away or accepted. Or every lack of electron is accepted as an accepted electron. And then the Lewis structure represents what it looks like, and then we can finally count how many of each that we have to figure out the formula, the molecular formula. There we go. That's as difficult as it gets. We can do further examples another time.